Okay, 2.6 is about the mean value theorem. And what we're going to first do is we're going to focus on visually the idea leading into the mean value theorem. And then we're going to talk about intuitively why it makes sense that this is true. So what I want you to do first is if you look at these graphs below, I want you to sketch at least one tangent line. But if you can sketch more than one, sketch as many as you can. Sketch one tangent line to the curve that's parallel to that dotted secant line that's going through the endpoints. So go ahead, pause this video, sketch your tangent lines. Okay, so pretend my lines look nicer, but it looks like on number one, we could draw one tangent line that is parallel to that dotted secant line, the secant line that's going through the two endpoints. On number two, the problem is it looks like maybe where that tangent line would be is where that hole is. So no, we can't find any here. And something to notice is that there's a hole or a discontinuity happening, and it seems like that is the issue here. On number three, the only place where it seems like we could potentially draw a tangent line would be along the x-axis, and this graph looks like it has a sharp turn there, which means it would not be differentiable, so we wouldn't be able to have a tangent line. So none here because of this sharp turn. On number four, it doesn't seem like we're going to be able to create any tangent line because it seems like any line that we tried to create would actually intersect the function 2 times. Therefore, it would not be a tangent line. So this also seems like we can't create any. Number 5, it looks like we could potentially come up with 3. And again, these are me sketching attempts at coming close to that same slope. And number 6, it seems like 1, 2, 3, 4, 5 potential tangent lines. So I want you to look at all the ones where we were able to come up with at least one line and all the ones where we couldn't, and see if you can identify some criteria for what allows us to do this. So a couple things I noticed about all of the graphs where we could not find a tangent line is that there were issues with derivatives, or there were issues with continuity. On 2 and 4, those were both not continuous along the entire interval that we were talking about between the endpoints. So it seems like, and then all 3 of the ones, 1, 5, and 6, are all continuous everywhere. So it seems like we have to have something continuous. That doesn't explain number 3. Number 3 is definitely continuous along that interval. The issue was that sharp turn. So the 2 criteria that seem to exist here is that we have to have a continuous and differentiable function in order to draw this tangent line. So let's talk about what that means, how that ties to the mean value theorem. What does the mean value theorem even say? Before we formally get into the idea of the mean value theorem, I actually want to just get you thinking about intuitively what we're about to formalize. So I want you to think about, we're looking at a trip in a car, and let's say that the y-axis is our velocity, we're moving in miles per hour. The x-axis is our time. And let's say, I'm not going to put numbers on here, we start the trip, maybe we are driving slow through the city, then we get onto the freeway, then we get off the freeway or switch freeways. Let's just say that our path looks something like this curve. Now, if we could think about the secant line between the endpoints, and we could find the average mile per hour we were driving, right? The slope of the line between those 2 points. Let's just give that a number. Let's say the average speed we were driving on this trip was 55 miles per hour. And to find that, we just looked at the slope, right? We looked at the average rate of change. This y2 minus this y1 over this x2 minus this x1. That would give us our average speed on this trip, our AROC. Now, if we averaged 55 miles per hour, it's likely that at some point we were going slower than that, and at some point we were going higher than that. But if you think about our curve, if we never stopped along this whole curve of traveling, at some point in time, we had to actually go through and be driving exactly 55 miles per hour. So at some point, the slope of this tangent line had to be exactly the same as the slope of the secant line. So we were talking about that visually looking at those first 6 graphs, but thinking about this more theoretically, if I averaged 55 miles per hour on a trip where I was driving and did not stop, at some point in time, I had to actually be driving exactly 55 miles an hour. And that's what the mean value theorem says. So let's formalize that. Just like we pointed out when we were looking at those 6 graphs at the beginning of these notes, there are 2 very, very important requirements in order to use the mean value theorem. We need to be talking about a continuous function on a closed interval, and we need to be talking about a differentiable function on the same open interval. So anytime you're using the mean value theorem, you must state that the function is continuous and differentiable. Just like with the intermediate value theorem, it's not assumed. You have to state it. You don't have to prove it. You don't have to say why you know it's continuous and differentiable. You just actually have to state it. So for a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b, there will exist at least one c value such that the derivative, also known as the instantaneous rate of change, is actually equal to the slope of that secant line, or the average rate of change. So what the mean value theorem says, just very simply, is if we have a continuous and differentiable function, at some point the average rate of change is going to be equal to the instantaneous rate of change. So mathematically, if you're given a function that you know is continuous and differentiable on an interval, you can use this mean value theorem to not only say that there's a point where the derivative is equal to the slope or of the secant line, or a rock, but you can then actually find that particular value. So let's look at a couple of examples. Directions: determine if the mean value theorem can be applied. If so, find the c values that lie within the given interval. So again, you have to state that the conditions are true. So I'm looking at number 1, it's a polynomial. That means it is continuous and differentiable. So I need to make sure I go ahead and state that. So I'm just stating f of x is continuous and differentiable, therefore MVT applies. So since f of x is continuous and differentiable, we can use the mean value theorem. So you need to state continuous, you need to state differentiable, you need to say, so MVT applies. Let's make that a little bit more readable. Okay, so now I need to do 2 things. MVT says that at some value for c, the instantaneous rate of change and the average rate of change are the same. So let's start by finding those 2 things. The average rate of change is going to be the slope. So f of 2 minus f of negative 3 all over 2 minus negative 3. That's going to give us 3 minus 18 over 5, which is going to be negative 3. So the average rate of change is negative 3. The instantaneous rate of change is just going to give us the derivative. So let's just find the IROC, which is f prime of x, which is going to be 2x minus 2, just taking the derivative using the power rule. So what I am allowed to do because of the mean value theorem is say that there is some value where 2x minus 2 equals negative 3. We can solve for that to just get that x is going to be negative 1/2. So the c value that we're looking for on number 1 is negative 1/2. So state that the conditions are met, find the average rate of change, find the instantaneous rate of change, set them equal to each other to find the c value if you're being asked to do that. So go ahead and pause the video on number 2, see if those conditions apply, and go through that process. So the first thing to note, f of x is not continuous everywhere. On number 1, I just said f of x is continuous and differentiable, so MVT applies. On number 2, f of x is definitely not continuous at x equals 0. So what I can say, looking at the specific interval that they're giving us, is that f of x is continuous on that closed interval and differentiable on the open interval. Therefore, we are allowed to use MVT. So now I'm going to go ahead and find the AROC and the IROC. So the average rate of change is going to be f of 2 minus f of 0.2 all over 2 minus 0.2. And if you plug in numbers there, f of 2 is 1/2, f of 0.2 is 5 over 1.8. So that's going to give you negative 5 over 2 as your average rate of change. Instantaneous rate of change is going to be the derivative of that. F prime of x is just going to be negative 1 over x squared using the using the power rule. So then we can go ahead and set those two things equal to each other. Negative 5 over 2 equals negative 1 over x squared. And when you solve that, you're going to get plus or minus 2 over 5. And so we just want the positive version because that's what's inside this interval. And sorry, I said 2 over 5. Oh no, I did mean 2 over 5. So this is going to give us the square root of 2 over 5 is going to be that C value. Go ahead and pause the video and try and do number 3. So for starters, f is definitely continuous on the closed interval from pi over 2 to 3 pi over 2 and differentiable on the open interval from pi over 2 to 3 pi over 2. Therefore, MVT does apply. So we can go ahead and find the average rate of change, the instantaneous rate of change, and set them equal to each other. So average rate of change, we're looking at f of 3 pi over 2 minus f of pi over 2 all over pi over 2 minus 3 pi over 2 minus pi over 2, which is just going to be pi over 2. This is going to give us 0 over pi over 2, which that whole thing is going to become 0. So the average rate of change is just 0. Next, we can find the instantaneous rate of change. The derivative of cosine of x is negative sine of x. So we're looking for when negative sine of x equals pi over 2. I'm sorry, when negative sine of x equals 0. On the interval between pi over 2 and 3 pi over 2. So that's going to just be pi. C is equal to pi. There are other places that sine equals 0, but not within that interval. All right, the very last question. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway. As a truck passes the first patrol car, its speed is clocked at 55 miles an hour. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Prove that the truck must have exceeded the speed limit of 55 miles per hour at some time during the 4 minutes. So we're going to start with the assumption that this path this truck is driving is continuous and differentiable. So I'm just going to say path is continuous and differentiable. He's in his truck. He's not moving in a sharp turn. He's moving on a continuous path for this very short amount of time. So I'm going to just I'm a more visual when it comes to word problems. We're looking at one patrol car, and then we're looking at a second patrol car. They are 5 miles apart. So if we want to think about his average rate of change, we can think of the first patrol car at the point 0, 0. So 5 minus 0 over 1 over 15 minus 0, since he was going, this was 4 minutes later. 4 is 1/15 of an hour. So that's going to give us that his average rate of change was 75 miles per hour. Based on MVT, there has to be some moment in which he was going 75 miles per hour. We don't even have to, it doesn't ask us what is the specific moment. So you can conclude, and this would be a nice complete sentence to fit on the bottom, which I have not saved myself enough room for. But since MVT applies, at some moment, this truck was driving 75 miles per hour, which is greater than the 55 mile per hour speed limit. Therefore, at some point, he was exceeding the speed limit. So mean value theorem, the important things to remember when you are using it, you must state that the conditions are met, the continuous and differentiable. You need to find the average rate of change, find the instantaneous rate of change, and when applicable, set them equal to each other to find that particular C value. So I hope this video helps you understand how to use the mean value theorem and why it works. Thanks for listening.